Hi, I want to make a video talking about the Windows on ARM, right? Calling a Snapdragon one, because there's a lot of misconceptions on Snapdragon versus Lunar Lake, right? We know it's just recently how they had Lunar Lake here. Hope I don't lose something. I really hate this shit. Oh, no. Now, because there's a misconception to say Lunar Lake is as good or even better than the Snapdragon, right? Oh, okay. Shit. Fucking global speed. I just think that's just ridiculous. It's just global speed. Can we just disable it here in this website? Okay. Lake versus Snapdragon. Now, because there's a lot of claim to say is Lunar Lake has a very good power consumption, even better than Snapdragon. That's just untrue. Okay, because like I said before, right, of this problem. So we have the SD span, which is we're gonna use more registers because it's not past my memory, and you can just go and search it. Okay, because there's a lot of so-called evaluation that just talk about Snapdragon versus Lunar Lake, but when they do this, they usually do it very wrong. Either just using a translation, using x86 emulation to say, hey, it's just the performance bad, or just saying other thing. Now, I'm not trying to here to defend the Snapdragon's software compatibility. I mean, it depends on who you ask, right? For people like me, it doesn't really matter, right? I use it quite well. Maybe it's a problem for you, right? That's not my point of this video. I'm not trying to define it. What I'm trying to say is that there's a lot of people just saying Snapdragon has better, this Lunar Lake has better power efficiency than Snapdragon, like Geek1, right? They just did it. The problem is that they run x86 emulation in the background with that is a cloud music, right? That was an x86, I think probably 32-bit, I don't know. An emulation of the app. And then they try to evaluate that with evaluation of power efficiency. But here's the thing here is that when we compare things, we need to compare apple to apple, right? We need to control all the variables. We need to control, both of them need to be native. Okay? Needs to be a native. Okay. I know some people say, oh, I just run a lot of translation app. It's not unfair. Well, it is unfair because there's no technical barriers to say I'm not allowed to compile it, right? It just maybe it's not here, but it's not like some Chromebook, right? You basically cannot run programs. It's not like that kind of thing. So we're just trying to compare apple to apple. The problem with x86 is a problem like this, okay, which is that the span is not passed by memory. It's passed by not passed by register, but passed by memory. You see, right? So you can see there are memory access just to pass the span. Well, the reason for that is because based on Windows x86 64 calling convention, the calling convention asks the code to pass the structs that is larger than 8 to be 16. And unfortunately, C++ types like span and string view, they are 2 pointers, right? So 2 pointer types based on Windows x86 64 calling convention will pass by memory, which is not an issue on on Linux, on Windows. Okay, I'll just first try to explain my point. And another one, which is the binary. Just look at the binary size. I think probably we're going to see the same results, right? Okay, this is probably not quite fair because this is larger, right? Well, it's probably not quite fair because x86-64 is quite established. We really cannot see that. But even with Apple Silicon, we can see its Intel one is larger than the Mac one. Okay, let's just not talk about the Apple Silicon. Let's just talk about LVM. You just can try to find any project. Okay, let's just release binaries for both AX64 and x86-64, right? Now let's just try to compare it. Now see all these binary size. The AX64 is always this. The x86 is always larger than AX64, which is ARM64, but it's actually technically called AX64 because ARM is a different architecture, ISA, than AX64. So we have AX64, Linux Android, which is larger, but which is smaller than x86-64, right? And it's not a small percentage, it's a huge percentage. You notice I'm compressing it at maximum level. So the real gap is much larger. Even this one you can see it's a very clear gap. And if you compare to compare x86 Linux GNU with, okay, it's probably not a good idea. But let's just compare x86 Linux Muscle, right? We'll see, with Muscle, it's still much larger. And we can see, if we compare x86-64, we could just use any of them. You could just try to see all of them, the x86 is larger. Okay, we'll just use the x86 Linux Muscle as an example. Okay, you don't need to know what is Muscle. Okay, but you just know they're just the same platform with different architecture. Okay, so let's just try to compare these three binaries. Just compare the binary size. Okay, just purely binary size. Okay, let's see. x86 is, I compiled it. I don't think I'm cheating. I have no reason to cheat, right? I have no reason to make it better because why would I do so? You can try to check any project, you're gonna see the same result. Okay, let's just see that one. Now we can see the AX64 and LoongArch, which is the Chinese architecture. I don't know whether a lot of people know that or not, which is somewhat like RISC-V, but it's not RISC-V. And if we compare these three, okay, we'll also put RISC-V here. RISC-V and RISC-V is another bullshit. But you can see the AX64 is the smallest one. Then there is LoongArch64. Okay, then we see x86-64 is larger than any of them, any of other architecture for the same platform. Now, you might say why the AX64 is larger than LoongArch64 and RISC-V. Well, the reason AX64 is smaller than LoongArch64 is because AX64 has one thing called fusion instruction, I think is that they can fuse two instructions, simple instructions together in one instruction. But it has a huge downside is that the instruction, the decoding becomes much difficult. And x64 also has something like carry flag, the flappy registers, that LoongArch64 doesn't have. So the LoongArch64 actually has the same amount of registers, but it is much simpler. Which is that even they have a basically very close binary size, I think LoongArch64 would outperform AX64. So they're at the same level, right? But if we look at x86-64, or RISC-V is also larger. RISC-V, you can look at other platforms, probably even bigger in terms of gap, right? In terms of gap. The reason is that RISC-V is a very fragmented instruction set. the they have a bunch of extensions which is not by default applied to the GCC and LVM. To ensure your code could run it, should LVM could run it, even when I compile it, it's still very fragmented, you know. I don't think there's any way you can solve it because of the fragmentation. If we not have a fragmented RISC-V, we won't even have LoongArch64. The reason we have LoongArch64 is because RISC-V isn't good. But here we'll just compare Lunar Lake with Snapdragon, which is the AX64 versus the x86-64, right? Now we can see it's just much larger than any of them. Right? Now RISC-V is probably not a good idea to compare with because I think there's a lot of different, because RISC-V basically bullshit instruction set. We're not compare RISC-V here. We can see the x64 is just larger than LoongArch and AX64. Now tell me how are you going to be more power efficient when you literally need to execute more instructions? Plus, we know x64 is mostly used for Windows. Sure, sometimes you're going to say I'm running on Linux, but even with Linux, you're not going to get rid of a Windows thing like UEFI, right? Your booting needs Windows API. You need wine, right? Wine, you probably also run virtual machine, whatever. But wine is probably something very common because if you want to ship binaries, particularly games, if you're running games on an x64 Linux machine, you need wine, right? The wine will still use Windows API, right? So we can just say that cost just adds directly to x64. So not only you need to pay for the cost of that part, also the part of calling convention, Windows calling convention. Now you might ask why x64 is larger than the x64. Is that just because of encoding? Well, maybe, but a larger problem is that x64 only has 16 general purpose registers, which is very fundamental, right? You have RAX, RBX, RCX, RDX, RSI, RDI, whatever, RSI, RDI, REX, RBX, RCX, RDX, RSI, RDI, RSP, RBP, I think. Then you have R8, R9, R10, R11, R12, R13, R14, R5, R15. You have these 16 registers for x86-64, right? Well, if you look at, for example, AX64 or LoongArch64, I think LoongArch64 is probably, or LoongArch64 or AX64, whatever, they have R1, R0, R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, R11, R10, 12, R13, R14, R15, R16, R17, R18, R19, R20, or whatever, just whatever we are calling RISC-V or AX64. You have 32 registers. All some registers make this result. But you get my point, is that they just have much more registers, right? Just double the general purpose registers. And when you don't have enough general purpose registers, what ends up is that the compiler needs to move your code, move your data from the register into the memory, perform the computation, and then copy back, load back of the data from the memory into the registers. And that part is a very expensive part because memory access is very, very expensive nowadays. Even if you have cache, even if you have all these fancy things, they're still very expensive. Because even you're talking about cache, how do you gonna ensure the consistencies between your different cores, because we are now using multiple cores, the multiple threads. You need to ensure all these registers are synchronized in the right way, right? The memory, well, probably not register part, but the memory part needs to be synchronized across every core. So the overhead is much larger than even on paper. Even from pure instruction perspective, it is much harder. The reason I know that is because I just used to write a code called, I think, write SHA-5 to 112. I think many people know that, right? The checksum algorithm. If you look at it, what OpenSSL did on x86-64, they just handwrite assembly. Because the reason they're handwriting assembly, well, some people are saying handwriting assembly is because they want to ensure you have a consistent time, right? Because if the instruction is just the compiler does something weird, your code might not execute in a deterministic time frame, right? They could leak secrets. But we're not talking about the leak secret part. There's also another part with it, is that the compiler just simply cannot allocate registers very well. So that's why my fast-IO library cannot perform as good as on x86 currently compared to ex64, because on ex64, I can guarantee you my algorithm outperforms OpenSSL assembly, and you can just prove it by yourself because the instruction literature is better. But since you don't have enough registers, the compiler cannot generate the instructions very well. And that creates a problem, right? Because your compiler just do too much trivial moves. They just add up cost to the cost of every function, that just end up being your instruction literally needs to execute more. It's much more. It's not just small percentage. Now, the Intel is trying to fix it with the Intel new APX instructions, Intel APX, okay? Which is what Intel called it just advanced performance extensions, right? They know that's a problem. And they're talking about exactly what I'm talking about. And they said if we increase the register number, double the register number from 16 to 32, we're gonna have 10 fewer loads and more than 20% fewer stalls for the same code compiled for the x86-64. That's a huge difference in terms of power efficiency, right? Because we know power, it's just very expensive when you are just triggering something from loading from memory, right? We know that Lunar Lake doesn't have APX, it doesn't support APX. So that's a huge problem, because if you don't support APX, from your latest CPU you published here, you're literally buying some CPUs that already gets obsoleted. And let's just be very clear. I want to talk to you that Lunar Lake is obsolete because it doesn't support. Obsolete because it does not support APX, right? Just by words, right? Let me just read it. Intel doubles the number of GPR from 16 to 64, which is that Intel tells exactly what I'm talking about, right? So you have a huge problem because you don't have enough. You don't have enough GPU general purpose registers, and then you don't have the problem of that. How do you even compete with your Lunar Lake with Snapdragon? You don't, right? Okay, so they're telling you, you can just read their own word. They literally tell you that APX can just greatly increase the power efficiency of x86-64, but they're not putting that in Lunar Lake. Which is why I don't use, I just buy Snapdragon, right? Because I know that they're fucked up. All the existing benchmark, even before I buy the machine, probably Lunar Lake, I don't know whether the Lunar Lake wasn't even a thing. But I know, well, I knew Lunar Lake will be, they will put Lunar Lake here. They will release Lunar Lake. But I don't think it's going to outperform the efficiency of a Snapdragon. That doesn't mean I'm against x86. Absolutely not, because I'm not trying to just join the debate with CISC versus RISC. I'm not doing that. I'm just saying, just from the pure instruction perspective, from a programmer perspective, I think that's a huge problem. Okay, another problem, which is I replied. I think a lot of you also know that is the STD span isn't zero cost on Microsoft API, right? On Windows API, because the Reddit, right? They banned me for talking about so now. Yeah. So the compilers and the API, we can see that if we talk about, if we go at Windows API, Microsoft will tell us that on x86-64 calling convention, is if your any argument doesn't fit into 8 bytes, which is 1, 2, 4, 8, will be passed by reference. That's a huge problem for STD span, right? Because C++ has these fair pointers. Not just C++, many other languages have that too, but like C#, whatever. So you're gonna have a global cost. Now you somebody say, I'm just writing Rust. Well, I think Rust probably doesn't have the problem, but you will have the problem indirectly because you're using Windows, right? You're on the platform, if you're just designing your own calling convention without trying to build on top of existing calling convention, that's gonna add a huge amount of cost when you try to call into Win32, you know. Your Rust API will have a very high cost when you try to call into the Win32 frequently. So I don't think you're just using Rust, you can solve the problem. So we can see that here we have the problem is that we have this type of x2 span that it doesn't get passed by registers. You have this problem. But what I was wrong at this point was that I thought AX64 also had this problem, but it turns out it doesn't have, right? So now I can just show you here. I can just literally show the assembly. We can just check assembly, and you can verify yourself with either my 5-star library or with a standard library. Okay, Snapdragon, whatever, we'll just call it in a file. We just get a span. Well, we can use first use C+ STD span, okay? Because maybe we need 2 different span implementation. Maybe that is because one implementation has issues, another doesn't. Right? So we're going to try span. What we're going to do is very simple. We're going to call foo. We're going to call, for example, whatever, right? We just call it sp. Okay, we need no except probably, right? And we're going to have another one called bar. We're going to call std span. Further, size t, right? We just gotta have old style code. I'm going to write a lot. Gonna call into here. Let's just assume that we have an external function, right? What we're gonna do is just call it sp.data. We're just gonna transfer this this span into the the function. Then we're gonna do is call baz. We're gonna have int star sp size t n, which is just directly call sp n, right? Now we can just try to check assembly here. Okay. See, here the thing here is quite funny is that I'm actually just using the Edge browser. Okay, I'm not, this VS Code is Edge browser. No. So we're gonna compile it. We're gonna first compile with x86, okay? So we're gonna use user profile. I think maybe, well, we can even check assembly of other architectures, maybe. Okay, then we'll just try to check AX64 and STD span of AX64, okay? Okay, we have these 2 instructions. Let me check whether we can check other ISA, like LoongArch. I don't think we can LoongArch, but maybe we can do something here, okay? but just calling target. Maybe we could. Oh, we couldn't. Okay, that is. Maybe I'll have a way to just make it supported. Unsupported architecture. That's interesting. Just, I think maybe we can make it work, but okay, let's just not talk about that. Just first check this too. We're gonna compile the instruction set. We're gonna check the assembly, okay? To prove a point, I'm just gonna explain to you here. Now we can just check. We have our bar function and foo function, right? So here is the foo function, which is quite weird with the Windows calling convention. We're using client. We're not even using MSVC, okay? Where's the instruction? Oh yeah. So you can just check. It's just B, right? Just you can see the function is just very simple. It's just B. It's just a tail call. It's B. But if we look at on Windows part, yeah. If we look at the second function, is like a tail call, right? You just direct jump. But for this part, it isn't. Right? It's move RCX, which is we try to extract the data from the RCX registers and move into the REX. And then we just move the registers. We just extracted the pointer because the span is passed by memory, right? So the span is passed by memory. The span, we need to extract the data from the span. Here we extract data from the span, putting the register called REX, and put the second register, which is size, into RDX. And then we do a move, because I think what's happening is that, oh yeah, the first parameter will be passed by ICX. So the compiler does is that it tries to move the data we just moved in and passed into the RCX. So we're gonna, using the data, we're just loading and override it. And then we do a jump, because now we can do a tail call. So you can see it needs 2 more memory access. While in the, which is Lunar Lake, the code you're gonna execute, you're gonna have just for to span, you're gonna do every function, you're gonna do something like this. Well, in the Snapdragon one, you don't. You just do jump. Okay. So that's a big difference, right? Just from a pure instruction perspective, it's a huge difference, right? There's no joke. It's just be huge difference. So, yeah, that's why. So just from this part, we can just see there's a very similar thing that the Windows calling convention doesn't have. Now, I think probably you'll have a Linux or Mac, like whether I have Mac, whatever. Even on Linux, you don't have the problem, okay? If you're on Linux, you don't have the problem, x86, but you are not free from Windows calling convention, because like I said, UEFI, Sigwin, and many other x86 use it, your Linux will more or less get affected. Sure, maybe not as big as Windows does, but you're gonna still get affected, particularly if you're running Windows application on your Linux, which is very common, right? Because we have Wine. You probably run your games, right? You're probably just running games and see how quickly the battery is gonna drop. Your browser, maybe that's a browser, maybe like a good example, but games is probably a very good example. Or you probably run some Windows applications like Fuba 2000, running some like no plus, whatever. You're running Windows application on your Linux machine, you're gonna suffer from the same problem too. So it's not a problem just on Windows, okay? We are using it as Windows as example, but it's actually a globalized performance job on Windows. Just one example. And also the lack of GPR, because I like it said. So actually, it's just from pure instructions perspective, they have a huge disadvantage. Now, do we have data to back up claim? Well, if we look at Snapdragon versus, I think probably we have this benchmark on here. If you look at all these benchmarks, Lunar Lake is alive. Let's just see what these things are talking about. Now here the largest problem for Lunar Lake is that if you're not using on power, the Snapdragon will provide you close to peak performance of battery. But Lunar Lake will suddenly have a huge performance drop from 15 to 60, 56%, depending on your workload. So this is the largest part, because the Lunar Lake is just not quite efficient, and particularly on plugging, which is the part we care about because we talk about battery life, right? Sure, sometimes good plugging is also very important, but the largest problem for us right now is you have laptop, right? You have these mobile devices. You want to know the power efficiency of your battery because you don't want to charge it too much, right? You don't want to overheat. Here, the Lunar Lake just doesn't perform quite well. Now, there are part that is correct that Lunar Lake is talking about, that Intel is talking about. Probably a lot of people pointed out the Snapdragon is that it has poor GPU. The GPU isn't good. The GPU isn't a quality GPU, right? But I think this is probably gonna fix in the next generation of Snapdragon. But it doesn't really matter. What I want to say is that, just purely from power efficiency perspective, the CPU performance perspective, Lunar Lake is nowhere comparable to Snapdragon. Plus, you have basically double the cost. Now, if you look at the Walmart or Best Buy, they're gonna sell you at $400, $794, $99 for this machine, right? My machine. Plus, you can just go in and, like I did, just replace your hard drive. Then it'll take you another $140 for the Cosol. Let me just check my device manager. Yeah, there's 2 terabytes of hard drive. Yeah, using this Cosol MP600 Mini with 133. Like if you look at Lunar Lake, it's gonna cost you at least $1,500. So even from cost perspective, you have basically double the cost, right? You're doubling the cost, and then you're talking about performance, right? And you cannot even compete with the power efficiency here. Right, the power efficiency is just so bad on Lunar Lake. If you look at Lunar Lake Ultimate battery test, which is, I don't want, because I know it's gonna be bad, so I'm not going to just buy a Lunar Lake and benchmark it, because there's no reason to believe it's gonna be good. Okay, so we're gonna see that on this benchmark, this chart, the Lunar Lake is so bad. Now we can see just on the balance mode, which is probably something we care about. The Snapdragon is literally 3 times more power efficient than Lunar Lake. Okay, that is just insane. And if you go to the balance mode, it's probably high performance mode, right? It's twice much as more power efficient. And you see the Snapdragon is even more, like this machine's power efficiency is even better than MacBook Air M3. These are a lot of people saying, oh, Snapdragon sucks compared to Apple, which is another bullshit, right? Because I have Apple Silicon here. This is my Mac M4 Mac Mini, and to say that the Mac doesn't need x86 emulation or something, that's just literal bullshit. I have tons of applications that needs to do that. It's no way to say it's smaller than Snapdragon. This machine has helped me. So some people say, well, let's buy a Chromebook, but Chromebook cannot do a lot of things I want to do, like just formatting a USB drive. I want to use Rufus, right? I want to just create a Linux image for my desktop, or create Windows image. I cannot do that on Windows, right? Oh, I cannot do that on Mac, right? I cannot do that on Chromebook.
3 and a couple of X.
There's no way you can do it on Chromebook, right? And also, it has x86 emulation, right? Sometimes it makes a lot of sense, right? Like one example, I just jailbreak my router, an old router that only provides artifacts of 32-bit x86, and they successfully jailbreak that raw router, which is not something you can do even on Mac. Even on a Mac, you cannot do that. Even on Linux, you probably can't do that because nobody has the source code anymore. It's just a binary I download, and it can jailbreak my router, and I can flush open WRT on it. And this machine can replace my hard drive, and now it has Android emulator, New, right? Now I even have Android emulator. Okay, I have WSL, I have Android emulator to say that this machine doesn't do a lot, it's just quite dishonest. It can do much more than, probably sometimes even more than Mac. Also, I don't need Mac because I have an M4 Mac Mini, which is much cheaper. Why are you using a Mac for that? Why do that, right? Here we have the Android emulator, right? We have Android emulator. And you see, the Android emulator even can run Windows on ARM, right? This Windows on ARM application. Now you can see it's just literally Android emulator. Cough ARC64, right? Also, my compilers compile myself. There are problems with some developers, they have the tools cannot work, but literally this is a skill issue because they are bad developers, right? That's basically what I want to say, right? They have no idea what talking about. Probably they're Java application, Java programs or some shit like that. Java, this just proves that Java is a terrible language, right? It's just a terrible language because it doesn't do what it's supposed to do, which is cross-platform, right? Which is why everybody's moving to web now, progressive web app or something like that. So here's about the video. Yeah, I hope you enjoy it. And I think I should explain quite in detail on why these problems, because there are two parts. Lunar Lake has much better GPU than Snapdragon, but it's not quite true in terms of power efficiency. Now, what about the future, right? When people say, can x86 improve? Well, I think it could. It could do a lot, like fixing and getting a new calling convention, like adding 32-bit GPRs. But we know that Intel is not in crisis. Their stock is basically crashed down. The company is in huge crisis. We have no idea to know whether they would fix it or not. I think they could fix it, but I'm not convinced they could fix it at this point. That's my major concern. And maybe they're going to fix it 10 years later, but first, probably their company won't survive even 10 years later. Right? The tariffs of Donald Trump are put on other countries are just huge, has a huge impact on the supply chain of India. Right? And they are not even outsourcing the workers. Their factories are still not set up. So we probably even able to see that Intel is going to fix it, even putting this APX into the CPU. They're not removing x86S, right? They're the simplified version of x86 either. They're not trying to fix the encoding, right? Screwed up. So we're probably not gonna see that. And yeah, and that's the thing. We're probably going to see that, and maybe Intel is just gonna be irrelevant, right? That's from that part. I think I'm trying to fix it. Because I'm introducing a new calling convention called WinCall, and I'm trying to implement it, which is basically for fix for x86 because I don't want x86 to die. But to say that the Lunar Lake can compete with Snapdragon in terms of power efficiency is quite dishonest. It's just dishonest, right? Now, what about the x86? We need APX and WinCall, and for the Snapdragon, it needs a better GPU, right? Because the GPU isn't good. And I think in the next generations of Snapdragon, will probably Surface laptop 13, something like that, Surface laptop 9. We're probably going to see the second generations of GPU, and you're probably going to see better GPU. We could probably not even see a Snapdragon from Qualcomm. We'll probably see NVIDIA, right? NVIDIA probably gonna because they are try to employ people for Windows or ARM, we're probably going to see more players like NVIDIA. NVIDIA is a big player, right? Well, if NVIDIA just go there and go ARM, and that probably makes a huge difference, right? So from that point of perspective, Intel has a huge problem. Plus, even AMD is trying to move to ARM too. Everyone is trying to move to ARM, right? Now, another good thing maybe in the future is that if everyone really moves to ARM, maybe Microsoft could actually put Windows ARM phone, right? I really want to see phones for Windows or ARM with phones. But okay, that doesn't mean x86 needs to die, because I think a lot of things they can fix. But currently, it's nowhere comparable to ARM in terms of power efficiency. Okay, I think this recording is quite long. I didn't expect it to be this long, but every time I do that, I'm just not quite explaining my words quite clearly. So that's it. Thank you for watching this video. If you'd like to subscribe, just subscribe, right? I don't really care. That's it.